So today we're going through related rates, and it's a big exercise, but it will start off reasonably easy and then it'll get progressively more complex, and towards the end there's some pretty hard questions. As far as our notes go, we'll probably definitely go through the first two, and then we'll see how you guys are feeling about it, and we might sort of pause there, get you guys to have a go at the exercise, and then come back and do the third one towards the end of the lesson or something like that. So it's going to continue on from what we did yesterday, and it's a big unit, there's 20 questions, right? So we will, in the coming lessons, there's some shorter exercises, so there's some opportunity in coming lessons to polish off this exercise, all right? So we are spending one lesson on it, we are spending just today on it, but there will be time in the future for you when we finish the lesson early to dedicate some time to it. So we're starting with this question here. I'm just going to leap straight into an explanation of it, and then we can see what the maths is that we're doing here. The image below, I've drawn it up here on the board, shows an elliptical shaped oil spill that is expanding in area on the ocean surface. The area of an ellipse is A is equal to pi times AB, where A and B are the axes of symmetry of the ellipse. The rate of change of the elliptical oil spill is given by dA on dt, where we're not given units here, so that's fine. We're just going to use units of measurement per unit period of time. It may be assumed that the elliptical shape is maintained as the oil spill expands. Okay, so that's one of the assumptions we're making. Okay, part A, show that this equation is true. So what we're going to do is we're going to differentiate both sides with regards to t. Okay, because we're talking about a related rate. That's something occurring over a temporal interval, isn't it? Over a temporal period. So we're going to differentiate both sides with regards to t. So this is what I'm going to perform first. We're doing d on dt of this. All right. So capital A is a variable because it's the area. Lowercase a is a variable because it's the horizontal axis of symmetry, and lowercase b is also a variable because it's the vertical axis of symmetry. So they're all variables in the context of the question, and we're differentiating all of the variables with regard to time. So on the left-hand side, we're going to have dA on dt. All right. On the right-hand side, we need to use the product rule. All right. I've got u is pi times a, and I've got v is going to be b. Okay. Pi is not a variable because it's a number. It's not changing. So u dash, when I differentiate, I'm differentiating a with regards to t. Okay, it's going to become pi dA on dt. Okay, so it's like yesterday. Remember, if we're differentiating y, okay, the derivative of y is going to be dy on dt. If we're differentiating y to the power of 5, what's it going to be? 5y to the power of 4, dy on dt. Okay, so that's what we're performing here, a bit like what we did on Tuesday. Okay, so we've got u dash, we've got v. So v dash then is going to be dB on dt. All right. So that means dA, d capital A on dt, is going to equal u dash v pi b dA on dt plus u v dash. Okay, so from here, to get what it's telling us to get, we're just going to need to do a bit of factorization and rearrangement. Now on the left-hand side, they've got dB on dt. This is the term that they've got on the left-hand side with the a. That's what they've got on the left-hand side. So this is what I'm trying to isolate, this term here. Okay, so we can see that from looking at what we've got there. So to start with, because it's on the left-hand side and to not involve negatives and stuff, I'm going to factorize pi, and I'm going to swap the left-hand side with the right-hand side. Okay, so we're going to have pi out the front, we're going to have b dA on dt plus a dB on dt being equal to d capital A on dt. Alright, so I've just swapped them and factorised pi. Okay, we'll multiply both sides by 1 on pi. can see the solution. Remember, this is what we're trying to isolate. So we're going to subtract this one from both sides. And we'll have A dB on dt is equal to 1 on pi dA on dt. Take away B d lowercase a on dt. There's some alphabet soup going on there. So that's what it wants us to show, right? Good. We've got it. Okay. So what is this equation telling us? Okay. It's telling us the rate of change of B with regards to T being equal to the rate of change of the area with regards to T being equal to the rate of change of the horizontal axis with regards to T. So they're all linked. All right. That's the rate at which they're changing. And we're going to use that. So B there says, consider the instant when the area is 12. The area is 12 meters squared. Okay, so we've got a unit for our lengths now. All right, all we need is one for time. Show that A is equal to 12 on pi times B. All right, so show that A. Now we know from the initial equation, A is equal to pi AB. Right? We have capital A is 12, the area is 12, and we can divide both sides by pi times B, right? Cancels, and we're left with A is 12 on pi times B. Now, if you've been looking at the exam question booklets, right, you'll see there's a lot of questions that are worth 1 mark that are super easy to show. Okay, so that means you need to be very clear about how you move from there to there. All right, so if they're only worth 1 mark, they're going to be picky. They want to see all of the working out very clearly. This is how it's done. All right, the area of the oil spill is expanding at 2 meters squared per second. Okay, so let's start listing some units up here. The area of the oil spill is expanding at 2 meters squared per second. So that means dA on dt is equal to 2. All right? dA on dt is equal to 2 when the area is 12. When the area is 12, dA on dt is equal to 2. All right, what else are we told? We're told at this instance, B is equal to 2. And we're also told the rate of change of the horizontal axis, dA on dt, is equal to 0.5. And we have almost all of the information we need to fill in this equation. Okay? So if we're looking here at all of the variables, we've got all of them except A. We don't have A. But we do know from here, A is equal to 12 on pi times B. So that means A is equal to 12 on pi times 2, which is equal to 6 on top of pi. So now we have all of the variables, and we are asked to find this one, dB on dt. So we're just going to write it out. Let's write all the numbers up there together, and then solve it. So we have, I'll write the equation and then I'll substitute the numbers beneath it. We have A dB on dt equals 1 on pi dA on dt. Take away B times dA on dt. So all we're doing now is substituting all of these numbers into this equation. All right. So we've got A times by dB on dt, that's what we're trying to find. A is 6 on pi. dB on dt, 1 on pi times dA on dt is 2. Take away B is 2. Yep. And dA on dt is 0.5. Okay. And then to get dB on dt by itself, we'll just multiply both sides by pi on 6. And we can calculate that exactly. What are we going to have here? We've got 2 on top of pi times by pi on 6. So that's going to be 2 pi 2 times 6 is 12 pi on pi. It's 2 pi and 6. Take away pi and 6. Which is 1 on 3, take pi on 6. Okay, so we've solved it there exactly, and we need a unit. All right. Now B is in meters, and we've got our time period is in seconds. So this is the rate of change in B in meters per second. Okay, so you can see how this unit's about some pretty heavy algebra, isn't it? Lots of variables that we're substituting in. Let's do a quick recap of what we did. Okay, we started with the area function, and we differentiated all of the variables with regards to time, and we rearranged to get this equation. Okay? Then basically from there, we're asked to find what's the rate of change of B with regards to time. And we're given all of this other information, and so we're just substituting those variables into the equation and processing. Okay, let's move on to the second one. If you did the exam booklet for the integration questions, this is a question that popped up in the exam booklet for the integration questions. So I thought it's a good place to include it because you notice we talked about exams integrating the different types of units. So part A here is going to be a recap of some integration for us. All right, we've got a glass manufacturer makes drinking glasses in the three-dimensional shape shown below. The function that describes the curve that is rotated around the y-axis, okay, so we have to be careful, is y equals x squared. One of these glasses is filled to a depth of k centimeters, where 0 is less than k is less than 4. Find the volume of water in the glass in terms of k. Okay, so we know, let's talk about a couple of things we've got here. Firstly, we've got y is equal to x squared. Now we are rotating this around the y-axis, which means we need the function expressed in terms of x. We need a function of x. So we want to isolate the x variable. We're going to have x is equal to the square root of y. Okay? And if we're rotating around the y-axis, it is AB, our function of y, okay, or our x value, our function of y. I'll put x here. AB, our function of x, multiplied by pi and squared, isn't it? That's what we get when rotating around the y-axis. Okay. Now, in this circumstance, we're going to integrate it from, we're filling it up from 0 to k. K is the highest that we're filling it up to. Pi times our function of x squared. And what are we integrating with regards to? Y, dy. Okay, let's process this. So firstly, the square and the root cancel. Pi k squared on 2. All right, so depending on how high you fill it up, if you fill it up 1 centimetre, the volume is going to be pi on 2. If you fill it up 2 centimetres, the volume is going to be 4 pi on 2, 2 pi. If you fill it up 3 centimetres, we're going to have 9 pi on 2, etc. So that's the volume for any value of height. That's part A complete. Part B. An empty wine glass is placed under a tap from which water is flowing at the rate of 1 centimetre cubed per second. Okay? So what that means is water is flowing in at 1 centimetre cubed per second. That's our rate of change of volume, isn't it? The rate of change of volume is 1 centimetre cubed per second. At what rate is the depth changing? At what rate is the depth changing? Let me have a quick sketch of it. Okay? What's the depth in this circumstance? It's this value, isn't it? It's the value of k. Okay, remember k is somewhere along here, how high we're filling it up, and the depth is the value of k. Okay, so if we have, what have we got here? This is the volume, right? I should put it there. This is the volume with regards to any value of k. So we're going to differentiate here both sides of this equation with regards to t. Okay, we're interested in what's the rate of change of depth when the volume's coming in at 1 centimetre cubed per second. So if we differentiate both of these, we've got dv on dt is equal to, there's no product rule going on here, but I'll pull the numbers out the front. We've got pi on 2, they're the numbers, and we're differentiating k squared with regards to t. The derivative of k squared with regards to t is going to be 2k dk on dt. All right, now what are we asked to find? At what rate is the depth changing? We're trying to find dk on dt when the glass is half full. Okay, we've got dv on dt. We're trying to find dk on dt. There's one more variable that we need. Okay, we need k. Now, there's two ways of interpreting this question. I was thinking about it on my way to work today. It says, at what rate is the depth changing when the glass is half full? So does this mean, what do you guys think? Does this mean when k is 2, or does it mean when the volume is half of what it is when it's full? My suspicion is because there's a bit of ambiguity, they would have awarded marks for both, okay? But I think probably the correct way to interpret it is when the volume is half full, right? Because if you fill it up 2 centimetres, it's not half full. Okay, you can see there's more volume in the top half than there is in the bottom half. Okay? So that means the trick here for us is going to be, what's the value of k when the volume is half full? Well, if we were to fill it up to the top, if we were to fill it up 4 centimetres, what's the volume going to be? Let's figure that out. If full, the volume is going to be, what's that, 16 pi on 2, it's going to be 8 pi. Okay, so therefore, if it's half full, if we're filling it up halfway, if half full, the volume is going to be 4 pi. Okay, now all that is to figure out what's this value of k that gives us a volume of 4 pi. So we have, what's the volume formula? Pi k squared on 2 equals 4 pi. And we're rearranging this 4k so that we can substitute it into this equation. I hope I've left enough space for this for you guys. So we're going to have k squared equals 8 pi on pi, and we've got k is the square root of 8. Okay, square root of 8, 2 root 2. Excellent. We've got everything we need to isolate dk on dt. So let's just perform the substitution right away. We've got 1 equals pi on 2 multiplied by 2 root 8 dk on dt. So we just divide both sides by that. We're going to have dk on dt is equal to 1 on 2 root 8 pi on top of 2. And what's it simplify to? 1 on top of root 8 pi. Okay, we need a unit. Depth is in centimetres, time is in seconds. Alright, so what does all of this mean? It means when the glass is half full, okay, so we have half the volume in the glass, water's coming out the tap at a constant rate of 1 centimetre cubed per second. That's how fast it's coming out. So we're saying, how fast is the height changing? Okay, because of this curved shape, look at it, isn't this amazing? Because of this curved shape, it's going to start off coming out, the height's going to come out real fast to start with, and then it's going to slow down as the bowl gets wider, because it's coming in at the same rate, but the volume which it has to fill up has to increase. And so this changes as it fills up. And isn't that amazing that we're able to figure out what that value is using these complex integration and differentiation methods? Pretty good. All right, I'm going to stop there because the next one's even like maybe a little bit harder. And I think the ones that you start with in your book, okay, so we've done some complex integration and rearrangements here. In the textbook, they start like this. They start, here's the equation, differentiate it with regards to t, now perform these substitutions. Okay, so they do start a bit easier than the ones we went through. So let's give it a go, and then towards the end of the lesson we can come back and do some together. We've got the volume, we've got a conical flask, and the dimensions are shown alongside. So when you fill it up with water, it has a height of 10 and a radius at the bottom of 5. And this value here is the height of the liquid. That's how much we're filling it up. And that's the diagram there. And then this value is R. Okay, what's the radius of surface area when we're filling it up? Okay, part A. Suppose the height is h. Show that the radius r of exposed water surface is given by r equals 10 take h on 2. So one thing this question doesn't say is, we're going to assume, for the purposes of this argument, that the volume is appropriately modelled by a cone. You see with conical flasks is that lip at the top, but for the majority of the volume, it is a cone. So we're going to assume it's a cone for the sake of this question. Okay, now what we have here, I'm going to abstract these two triangles. Okay, we have the height of the cone is 10 and the radius is 5. And we also have this triangle here where this value is r and this value is 10 take h. Okay, it's 10 take h because the height is 10, and if this value is h, then this distance has to be 10 take h. And so we're going to establish a relationship here with similar triangles. We've got r on top of 10 take h is equal to 5 on top of 10. And so what's that? R is equal to 10 take h on 2. Okay, part A, complete. Part B, hence show that the volume of liquid in the flask is given by this equation. So we have the volume is 1 on 3 pi r squared h. And we now have a value for h. It's this one here. Multiplied by h. Okay, so for this one, I'm not going to process that because it will take a little bit of time, but it's just expanding that, collecting it. There's something you do have to factorize, and then you end up with the equation that they've got there. Okay, so they're saying show that the volume with regards to h is this. Okay, so you can process that one yourself. Let's move on to part C. Part C, find dH on dt in terms of dV on dt, and hence state the units. So if you keep processing this and you get it to the form that they've got, you've got V is equal to pi on 3 multiplied by 1 on 4h to the 3, take 5h squared plus 25h. Okay, so if you keep processing it, that's what we end up at. So that's V. So we're going to differentiate both sides of this equation with regards to t. So we're going to get dV on dt is equal to pi on 3 multiplied by 3h squared dH on dt. Okay, so the 1 and 4 stays there. Derivative of h to the 3 is 3h squared dH on dt. Alright, over here we're going to have to take 5 times 2h dH on dt, and then plus 25 dH on dt. Close the bracket. Okay, we try to isolate dH on dt. That's what it says. Find dH on dt. So what I'm going to do, I'm going to divide both sides by, or multiply both sides by 3 on pi, and over here factorize dH on dt. So let's do that. We're going to have 3 on top of pi dV on dt. Alright, and then over here we'll factorize dH on dt. And what are we left with? Quarter 3h squared, take 10h plus 25. Okay, and then to isolate dH on dt, we're just going to shove this over here. That's 3 on 4. 3 on 4h squared, take 10h plus 25. Okay, so we've isolated dH on dt. Alright, so what have we done in this question? We've started with the volume equation they've given us. Okay, so this is just like the exam, right? Even if you can't crack that, you can still move on to the next part. You can use the equation they've given you, and we're asked to differentiate both sides with regards to t. We do that, we factorize dH on dt, and we're trying to solve for this by itself, so we just chuck that over here. There we go, that's what we end up with. Okay, now water is added to the flask at a constant rate of 40 millilitres per second. So we've got a dV, let's list all the things we've got. We've got dV on dt is 40. The height of the water is 2. Okay, that's all we need. We're just going to substitute both of those into this equation to get dH on dt. It doesn't say find it exactly, so we'll just smash that in the calculator. Alright, so I'm going to put 40 where the dV on dt is, and the 2 where the h is squared and h is. Yeah, that's 5.7.
4.77 for the video.
And we need to state the unit. So h is in centimetres, millilitres. Yeah, which is centimetres cubed per second. So dH on dt is centimetres per second. Cool. All right.